Physics World.
Hello and welcome to the Physics World podcast. That is the sound of two neutron stars colliding, but it's also the sound of the dawning of a new era in astronomy. When LIGO announced in February 2016 that they'd discovered gravitational waves, there was a promise of this new era of multi-messenger astronomy. There was a belief that now that gravitational waves could be added to the mix, there would soon come a day when we could observe a single astronomical event using optical telescopes, radio telescopes, gamma ray, gravitational waves and more. And scientists from over 70 observatories from all these disciplines from around the world announced in October 2017 that this new multi-messenger astronomy has begun. 130 million light years away, two dense neutron stars, each about the size of a city but heavier than our sun, crashed into each other, producing a huge explosion called a kilonova, sending out gravitational waves. Ripples in space-time, as predicted by Einstein, which travelled across these astronomical distances, passing through you, me and planet Earth in August 2017. Sending astronomers scrambling to make successful observation of those colliding neutron stars with optical, radio, X-ray, gamma ray, infrared and ultraviolet telescopes. Over 40 papers were published simultaneously across the disciplines, describing, amongst a host of other science, a new way to measure the expansion of the universe, Hubble's constant, and strong evidence that the majority of the gold and titanium in the universe is formed by these neutron star collisions. I went to the Royal Society in London, where a panel of scientists from the LIGO collaboration and other observatories gathered to tell the waiting media about this stunning discovery. Chairing the panel was the Astronomer Royal, Lord Martin Rees, and I had the chance to ask him where he feels this fits in the story of astronomy.
It's clearly an important breakthrough, and I think it's sociologically very important because it shows how you can make huge developments by very precise engineering in the gravitational wave detectors, which is quite amazing precision to detect anything at all, plus also international collaboration and multi-waveband astronomy to follow up the gravitational wave signal by looking for neutrinos and finding gamma rays, X-rays and visible light and all that. I think it indicates how astronomy is a very broadly based international and multi-technique subject, as is seen by the fact that one of the papers has 3,000 authors on it, which is about 1,400 from the gravitational wave detectors, plus people from the 50-plus observatories that have been involved in the follow-up observations. So I think it's interesting, and I think neutron stars, of course, were first discovered 50 years ago, and their discovery was really a big surprise. There was some speculation that neutron stars existed, but the fact that they were detectable as pulsars by having magnetic fields and sending us a lighthouse beam of radio emission towards us was something which no one really predicted. So I think the discovery was a really big surprise, and then the observations developed fast, and 7 years after the first discovery of a pulsar, the first binary pulsar was discovered. And once we knew that existed, then in a sense we knew that there must be somewhere in the universe events like the one that's just been observed, where two neutron stars get close enough by gradually losing energy through gravitational radiation that you get a sort of final spectacular splat when they merge, giving a black hole. And the wait's been very long, but it's very gratifying that at last an event of this kind has been observed. And of course it's important to us as astronomers, but I think it's also important for physics, because this exemplifies not only the international character of astronomy, but also how astronomy provides a way in which we can learn about the properties of matter under conditions far too extreme to ever simulate in a lab. And of course neutron stars supremely exemplify that in their densities, their strong magnetic fields and in their strong gravity. And so this exemplifies how even if one isn't interested in what's out there for its own sake, one is interested in testing the laws of nature right to extremes.
You've got all these papers in front of you, I presume, at some point in the last few days. Which are the ones that sort of most got your attention? You're going, okay, that's new, that's interesting.
Well, I think one has to give primacy to the gravitational wave detection itself because of the amazing precision that was needed in order to detect gravitational waves at all. And this particular signal was rather different from the earlier black hole ones in that it involved having a template covering more than 1,000 oscillations. The first gravitational wave detection, which was 18 months or so ago, was of two black holes of about 30 solar masses each. And that was such a strong signal that you could actually see in the raw data evidence for these oscillations. In the case of this object, that was not so clear. You could see evidence for a signal that was getting larger in amplitude and then disappearing. And then, of course, when they were able to analyse it with different templates, they were able to work out the period and everything like that, and the orientation compared to line of sight. So I think it's the gravitational wave discovery itself which is probably most remarkable. But, of course, we have got more out of it because of the ability to deploy the swift gamma ray burst satellite and all the optical instruments to actually study another wavebands.
Clearly, to create ripples in space-time which can be detected on a planet 130 million light years away, you need a phenomenally massive event. Prior to this discovery, all gravitational waves detected on Earth were made by colliding black holes, and all those detections have been made by LIGO and more recently Virgo. It's only through the development of these high-precision gravitational wave observatories that we've been able to open up this new way of observing the universe. And in the case of LIGO, a laser light is fired through a splitter which splits the light and sends it back and forth down two 4-kilometre long arms at right angles to each other. The light is then measured by the scientists at LIGO to determine if there's been any change in its length. If there has, then there's a chance that they've discovered gravitational waves, as if those ripples had passed through our particular point in space-time, then the beams in LIGO's arms will have wobbled. More from Lord Rees later in the podcast, but also on the panel that day was Dr. Will Farr.
I'm a member of the LIGO collaborations. I've been involved in a lot of the pieces of it, mostly on the gravitational wave side. This has been the most exciting 2 months of my career. It is rivaled maybe only by the first detection 2 years ago when we knew we had something big. It's the first time we've ever seen gravitational waves. But I personally found this to be more exciting because of the collaboration with our electromagnetic astronomer partners. Pulled in so many more people with so many more new results and such a richer data set to work with. But I think the thing I'm most excited about is the measurement of the expansion rate of the universe, so this Hubble constant measurement. It's the first time that gravitational waves are really contributing to a quintessentially electromagnetic question, this fundamental parameter that controls the size and the age of the universe. This is vitally important for cosmology. And while we're not measuring it as precisely as the existing electromagnetic measurements, we're on the scene now, and will be in the future measuring it that precisely as we accumulate more and more events like this.
I want us to get a handle on the timeline of these events, because in my head it was a bit like the film Contact with Jodie Foster, with the signal coming in and with the scientists scrambling to get to their computers to begin work on and follow up on that data as soon as they possibly could. And in reality, it turns out I wasn't too far from the truth.
The collision happened about 150 million years ago. So I meant to look this up and I didn't. I'm not a paleontologist, but I think that's of order dinosaurs.
Okay.
So around the time the dinosaurs were last on the Earth, the collision happened at this extreme distance, and then the waves propagate at the speed of light, as you just heard, within a million billionth of the exact speed of light coming to us. And then they hit in mid-August, August 17th. And now I guess it's mid-October, so that's about 2 months. The electromagnetic folks get phone calls and text messages from their satellites when they see the gamma ray burst. LIGO people get phone calls and text messages when LIGO sees something. And then the people who don't get text messages, you start to see emails. And suddenly there's 15 or 20 emails in your inbox. Everybody, call this number, let's get together, we're going to have a telecon and talk about what's going on. Within an hour, there were gravitational wave sky maps available, well within an hour. And before nighttime in South America, which was where the first optical observations were taken, we had updated sky maps with an improved position. So we were rushing to get those out so the observers could plan their tiling of the sky, because we knew immediately from the Fermi gamma ray burst trigger that, this looks real, it looks exciting, we need people to be looking, so let's get our data out there so that our partners can look. We all worked feverishly to analyze the data in the electromagnetic and gravitational wave spectrum and figure out what, quick results we could get from it, form teams, write papers, sometimes jointly with our electromagnetic colleagues, sometimes separately, individually, and then push out as much as we could in these 2 months before this announcement.
At what point do you go, right, this is the one where now we're in the future of astronomy?
So I think the event happened mid-morning, UK time, if I remember, and by the afternoon, I think, basically everyone who was interested was saying, this is real. This is the dream. Let's get everybody looking at this tonight. We need to do, throw everything we can at this because this could well be the one.
Okay.
And then, the sun goes down in South America pretty late. I don't know, 11 o'clock, something like that, UK time. And very soon thereafter, within hours, there's a bright dot in that galaxy that hasn't been there before. Okay. And at that point, everybody just went nuts.
So the gravitational wave detectors at LIGO and Virgo are online as much as they can be during their observational runs. Dr. John Veitch is a research fellow at the University of Glasgow and co-chair of the group which did the analysis of the data which came from this neutron star collision.
When they find one of these things, they send out an automatic alert to the collaboration members, who usually get a phone call or a text message to tell them that something interesting has appeared in the data. And then everybody jumps onto our teleconferencing software, joins the party, and they pick apart the observation as it comes in. In this case, we had to look manually into the data to check that there was a real signal there, because one of the detectors was slightly out of whack at the time, and that's all described in our paper. But lo and behold, the signal is clearly visible in the data. And we also received the Fermi alert shortly afterwards, so we thought this was a very interesting event immediately.
Yeah. Okay.
Now, personally, I was on holiday and I was test driving a new car, and I was happily test driving that car in Edinburgh when the gravitational wave passed through me and the car, and shortly thereafter I received a phone call, which I didn't answer, being on a test drive. But when I finished the test drive, I quickly had to race back into the action and try and help with the analysis and the coordination, especially as the co-chair of the group. It's mostly about making sure everybody has what they need to do the work properly. So the credit really has to go to the team as a whole. There's a collaboration of 1,000 people, of course. I feel very lucky that the first neutron star that we've seen is also been observed through basically every band of the electromagnetic spectrum. There's no way that we would have expected that to happen on the very first one. That's my main.
But if you're looking at what other people are doing from these data, other observations that other people are making, there's any papers coming out of this you're going, I want to read that one?
Yeah, actually, there are more than 40 papers published today. I don't actually know the total number. And of course, a lot of them were under embargo even from us, so I've not read most of them. I'm really looking forward to going to actually see what everybody else has been up to. But I think the gamma ray work, they must be enormously proud of having made that association as well, because this was long thought to be the central engine of short gamma ray bursts. So that they must be having a day to remember as well, and finally being proven correct.
Someone who has been working on the gamma ray aspects of this discovery is Dr. Phil Evans. Phil is a postdoc researcher at the University of Leicester who works on the Swift Gamma Ray Burst Mission satellite.
So Swift is a satellite that was a joint venture between NASA, the UK Space Agency nowadays, it would have been STFC when we started, and the Italian Space Agency. And it's a satellite which was originally designed to search for something called gamma ray bursts, which are the most powerful explosions known to humankind. And what's the problem with them is they fade very, very quickly. So what's really novel about Swift is it has a large area detector called the BAT, which looks for gamma ray bursts. It can see about a sixth of the sky at once. But then it's also got an X-ray camera and a UV camera on it. And it's got what was certainly at the time kind of groundbreaking, really, technology on board, so that when it detects a gamma ray burst with the burst alert telescope, it works out on board roughly where the burst is, and it works out on board whether it's safe to point the satellite to it. And if it is, it automatically repositions the satellite and starts taking data with the X-ray and UV telescopes. And that means that you can now, if you detect a gamma ray burst, then with Swift you can be taking data in the X-rays and UV, within 2 minutes of the burst, whereas before Swift it was sort of 8 hours as you had to get data onto the ground and then uplink commands to repoint satellites and so on. And of course, over recent years, because Swift is now just coming up to its 13th birthday, we've been looking at, doing other things that weren't in the plan when Swift was built, such as responding to gravitational wave triggers to try and find X-rays or ultraviolet emission from the source of gravitational waves. And the fact that Swift can move very, very quickly is extremely helpful for that, because when you've got a not very well located gravitational wave and you need to look at 300 different bits of sky before you get to the right one, the ability to move quickly between those 300 bits is clearly very helpful.
Phil told me how the mad scramble to get the data to follow up on those observations was from his perspective.
This was, when this came through, they told us straight away, we think it's a binary neutron star, which they could tell from their signal straight away with high probability. So we were very excited. We could see that it was a rare event in terms of the false alarm rate, so it probably wasn't noise. And Fermi had triggered on something within 2 seconds of it. The Fermi satellite thought it had found a gamma ray burst. So all of this immediately, it ticked every box. And so we leapt into action, not quite literally, almost. We had to grab the conference phone and phone in, because the software that we use to work out where and when we should point Swift in response to a gravitational wave trigger is something that I wrote, but the software that controls the satellite and that turns my output into satellite commands was written by my colleague Jamie Kenner in the US. So the very first thing we do is get on the phone to each other and start talking. What made this one a bit challenging was that at the time of the gravitational wave event, there was also some form of what they call a glitch in the data at one of the LIGO observatories. And that meant that in the initial analysis, they only had one detector, which was LIGO Hanford, that they could actually use the data for. And with one detector for gravitational waves, that doesn't really give you any direction for where it came from. So our error region was the sky. Which is not very helpful. You can knock it down a bit because the gamma ray burst detection from Fermi knocked it down, but the gamma ray burst detection was like 1,800 square degrees or something. Our field of view with our X-ray telescope is 0.1 square degrees, so that's 18,000 locations. That doesn't compute. What helped was that the gravitational wave signal has distance information in it, and even in the immediate thing where you've only got partial data and they haven't been able to run it through their full detailed processing, which takes weeks to run, they knew that it was fairly nearby, and they give us a sort of an estimate of the distance. And so what we within Swift do, and this is something that I've written papers on in the past about how to do this, is we say, well, hang on a minute. If this is 2 neutron stars within, say, 40, 50 megaparsecs, neutron stars to first order occur in galaxies, right? We know where most of the nearby galaxies are, so we don't have to search the whole uncertainty region. Let's just look at the galaxies in that region. And we just uploaded the commands to the spacecraft to do that, and I think like 2 minutes after those commands were uploaded and the ground station pass had finished, so we couldn't talk to the spacecraft again for a while, LIGO issued an updated position where they'd fixed the glitch and removed it. They'd brought in the Virgo data, and they've got this really good 30 square degree thing. So as soon as that happened, we just put the phone down and gone, oh, phew, and we immediately picked the phone back up again and said, right, throw away what we've just done, got to make a new observing plan. So it was a high adrenaline, slightly manic experience, but we got there.
So what are you feeling in those moments?
Well, plus pure terror, because you know this is the big one, and you're working on the fly, and These are not the sorts of things, when you're taking up a lot of spacecraft time, you can do some testing, but there are so many permutations, you can't test them all because you just don't have the spacecraft time to use it. And in almost every event we've found some subtle issue. Hang on a minute, it turns out that if you start observing exactly at midnight or something like that, it doesn't quite work. And so there's the terror of what if we mess this up, combined with the fact that, hang on a minute, there's this subtle bug we hadn't seen before. So me and Jamie are usually on the phone exchanging bad words with each other as we're debugging our code.
Okay, so when you wrote this code originally, is this the event you were hoping for when you were writing that code?
It is. In actual fact, ironically, this was even better than we were aiming for, and that's what causes some of the challenges, because what we think, and I would say that not everyone will agree with this, but I would say that the event that we've now detected challenges this preconceived idea. But we thought that you only see a gamma ray burst in a very small fraction of cases where your viewing angle is just right. So we thought that the likelihood of getting a trigger from something like Fermi at the same time as a gravitational wave signal was very unlikely.
That's one aspect of this discovery which is of particular interest, that we're not in the direct line of fire, if you like. I asked Lord Rees what the significance of that was.
Well, of course, the detailed properties of gravitational waves depend on the orientation, whether we're seeing it face on or edge on. But for gamma ray bursts, it's also interesting because it's been thought that gamma ray bursts, or at least the short ones, are associated with coalescing neutron stars. That's something which I've believed for 20 years, although the evidence has been not all that clear. If you have binary neutron stars coalescing with random orientation of angular momentum vectors, then only about 1 in 1,000 would be lined up so that we'd see the beam. Okay, and that's why people didn't expect that we would see a strong gamma ray burst from the typical object, because the gravitational radiation is not strongly directional, it's only very mildly directional, whereas the gamma ray bursts we suspect are concentrated in this very narrow beam. But most of the models suggest that the gamma ray burst itself comes from a jet with an angle of only about 10 degrees. And if you're not in that narrow range, then you won't see the strong gamma ray burst. Now, in this case, we are plainly not in the actual beam of the gamma ray burst. If we were, it would have been not merely a typical gamma ray burst, but about 1,000 times brighter than the typical one, because the distance of this object, although it's way beyond our own galaxy, is about 30 times closer than most of the gamma ray bursts, and therefore, if it was a typical gamma ray burst intrinsically, it would be 1,000 times brighter, 30 squared, than the typical gamma ray burst. And the fact that it isn't means that we are seeing some sort of weak, as it were, side lobe emission going out in a broader range of directions than the jet itself. And that's something where there are as yet no detailed models, so it'll certainly help those who are interested in gamma ray bursts to understand and try and model more carefully how the gamma ray burst occurs. And it's good news too, because most of us had suspected that we'd be unlikely to detect a gamma ray counterpart of these events, and that it would have been unlikely if they produced no gamma rays outside the narrow beam, but they produce enough that we are likely to see gamma rays from most of the binary neutron stars which are close enough to be detected by LIGO.
Among all those wonders of the gamma rays and gravitational waves and radio waves and ultraviolet, I find myself possibly even more fascinated by the fact that optical light was captured from this event. Dr. Kate Maguire worked on the optical telescopes and was part of the panel of that announcement at the Royal Society. I caught up with her a few days later, and way back at the start of this podcast I mentioned that this event is known as a kilonova. I began by asking Kate what that means.
So a kilonova is when you have two neutron stars, which are small, dense stars, and Einstein predicted that during their lifetime, they will get closer and closer together and emit gravitational radiation waves. So then they end up colliding, and in this collision of the two neutron stars, you end up with a kilonova. So this is when heavy elements are produced, and you see an electromagnetic counterpart.
What can you possibly see with optical telescopes at that distance?
It's actually reasonably bright, so brighter than you might think. So our kind of standard thing that we compare it to is type 1a supernovae, which have quite bright luminosities and can be seen to great distances in the universe. But the kilonova actually produce a lot of radiation at optical and near-infrared wavelengths. So some of the models predict it should be more based at optical wavelengths and some at near-infrared wavelengths. We've seen it at both for this particular object. And you see it both in the collision itself and then also in the wind that's emitted when the two neutron stars. You can have some kind of disk that is formed and a wind is produced by this. And you can see this radiation for a couple of days, so it fades off quite quickly. But it's bright and then fades away.
You get an email, a text message to tell you that these gravitational waves have hit?
Yeah, exactly. We get an email to say that LIGO Virgo have discovered something, and they normally give a sky area, and they say, we think it comes from this area of the sky, and then we go and point all our telescopes as fast as possible at that region.
But I don't the telescopes aren't free, there's people using them, so how does that work?
So there are two ways you can generally do it. Some people have time, which is called override time on a telescope. So they have a very high priority program that they've already agreed with the people who have the telescope. And they say, okay, no matter what happens, if a gravitational wave alert happens, we can look at this region of sky straight away. And then the other way is you can just get lucky, which is what happened to us. And we had 5 nights of telescope time just after the gravitational wave on the 17th of August happened. So we were ready at the telescope and we were able to stop looking at the boring supernovae and then look at this instead.
Yeah, I like that. Boring supernovae, yeah. Which telescopes were you using?
So this was the New Technology Telescope, the NTT. It's at La Silla in Chile, so it's run by the European Southern Observatory.
And so are you physically in Chile or are you controlling it from Belfast?
So it's a large collaboration. I wasn't physically there, but there were people. It's a pan-European thing, so there's about 160 members. It's called EPESTO, the Public ESO Spectroscopic Survey of Transient Objects, and a few people from the collaboration were there at the time.
Okay. And what were you doing at that time?
It was probably, just after lunch? I was probably having a coffee. So then we started to plan the observations for that night. Well, first of all, when the detection first went off, we didn't obviously know what galaxy it was coming from. So the first thing you want to do is try and tile the area in photometry and try and find something that's changed. And so a number of groups, not particularly us, but other groups, managed to identify this transient in a particular galaxy. And then we were on the telescope to be able to go and take a spectrum the following night.
So you take the spectrum and then you start analysing it. How do you analyse it?
So firstly, you just you get the spectrum out and you go, okay, in this particular case, it looks really weird. So we were like, this is really unusual. It doesn't look like any supernova that we've seen previously. We've been running this survey for over 5 years now. It didn't look like any of the other spectra that we'd seen up until now. And so we're like, this looks really weird. We think this might be it. And it had reasonable agreement with some of the models that people have predicted, the theoretical models for these kilonova events. So we got pretty excited pretty quickly.
Yeah, I imagine, yeah. Are you immediately thinking, okay, has this produced heavier elements? Is that what you're thinking? Or are you just looking at it with open mind?
So we knew a lot of the models predict that very quickly the transient will go from blue to red. And so this is what we saw when we looked at the light curve. So we got multicolor photometry. So that was predicted that it would drop off and that you see the red because it's producing the much heavier elements. You get a redder signature in the near infrared. So when we started to see this happening over the first couple of nights, it really matched very well with the theoretical models that have been put forward for the kilonovae.
So what did you find? What did you actually find?
So we took light curves and spectra of the object. So the first spectrum that we got, so the optical spectrum, so how the features vary as a function of wavelength, was 1.4 days after explosion. And it looks like from our spectral modelling that we can definitely identify lines of cesium and tellurium, which are kind of lighter, heavier elements. And then due to the redder colour, so this quick evolution from blue to red, we can say that it's very likely that you produce even heavier elements such as gold. So we don't have the clear spectral signatures of the gold, but the colour evolution can tell us that it's very probable that it was present and produced in this event. A lot of people have predicted models of what these events should look like, but obviously this was the first confirmation of what it looks like. And I think one of the things that's clear is that these events do evolve very rapidly. So they drop off in brightness very quickly after a peak. And so really we need to be taking shorter observations of the sky, so quicker, so repeats of the night sky, so that we can try and find these. So one thing we can do is also look for them without the gravitational wave detection. Just look for these events in both the previous data we have, so we can go back and look in our archive of events and see if there's anything that looks similar to this. And then also we can try and find it without even the gravitational wave counterpart. So that's something we're currently doing. But you need to adjust our survey strategy, so how we look at the sky, to try and focus on these particular objects.
Professor James Huff is a fellow of the Royal Society, and he was there on the day of the announcement. I caught up with him to get his perspective.
Well, I've been doing this for 46 years, looking for gravitational waves, all with the idea that eventually we would be able to actually contribute, to bring new knowledge in astrophysics. And at last we've managed to do so. So I find it quite amazing that with one event in particular, this binary neutron star, just what the impact has been right across astronomy, both from the first real observation of a kilonova on the other hand, to the fact that soon we'll be able to measure Hubble's constant, in a totally model-independent way, and hopefully in a few years' time to have enough accuracy to be able to differentiate between the two kind of rival values from Planck and from the standard the ladder way of doing things. So I think it's just amazing how much has come out. But then, of course, we didn't expect to see this, I may say, the binary neutron stars as early as this, because all the predictions had been earlier that it would need to wait quite a number of years. But then we didn't expect to see the initial black holes either. And that was a huge surprise, to see the binary black holes.
Yeah. What's your role?
Initially I started off, I suppose, working on the laser side of the laser interferometers, but then moved on to the suspension side and did a lot of the initial work on making the fused silica suspensions that really made the detection possible in advanced LIGO, allowed the low frequency performance to be obtained. So for many years I led the group that was doing that. I no longer lead it because I handed the group over to Sheila Rowan, who when I reached, or just before I reached retiring age. But I mean, despite that, I still work on it, because I still have a research contract that lets me continue. I just don't lead the group anymore, but I still contribute to the physics. And that area still interests me a great deal. How to get the fundamental noise in the suspension systems reduced to a level that allows the sensitivity overall of the detectors to be improved.
And so it's that kind of work that's led to this discovery, isn't it?
Yes, that's right. To a large extent. Not just that. I mean, our German colleagues. A lot of the work came from GEO 600, the UK German detector, where we pioneered. Our German colleagues brought in new lasers, used new lasers. They tested the ideas of thermal compensation, the signal recycling and signal extraction, resonant sideband extraction, and the silica suspensions. And these are all the things that we moved into advanced LIGO from the UK German GEO detector. And it took a number of these things, including, of course, also the beautiful seismic isolation systems that were developed at Stanford University, to allow the advanced LIGO to make the improvements it did. All these things together made the detection possible, but the fused silica suspensions have a special place in that.
A couple of years ago, when the first gravitational waves were discovered, everybody was talking about a new era of astronomy. I feel like we're living in it now.
Yeah.
Is this the first of one a year? Is the first of many?
I think this is the first of many. And of course, if we take the black holes, for example, there's so much you can do with the black hole observations once you have enough of them. But you need to have enough to be able to get an average of, to get a feeling about what's the spin, etc., like of the individual black holes before they merge. Because that gives you more information about basic cosmology and in the end, how the black holes are formed, and this may tell us more about galaxy formation, for example. So there's a lot of astrophysics to be done but we need more measurements, so we need more observations. And I mean, even with the present detectors, it's likely that I'd have thought within a few years we'll be seeing maybe a black hole, coalescence a week or something like that. And then, of course, that is what we want to do is to build more sensitive detectors still, and we have a plan to do that. To upgrade the LIGO detectors.
Okay. Oh, right, okay.
And to give us more sensitivity, which means we should be getting many black hole events, per week, and maybe we should be seeing neutron star events too, every week or so or something like that.
Really? Every week or so?
That could, I think, with the next stage, once not maybe not quite with this present set of detectors. I mean, well, we could, of course, it's possible we might get as much as one a week, but I would have guessed that would be very lucky. But certainly once we get to the next stage where we upgrade by a small factor the sensitivities, we should improve the rates. Well, that's very hard to tell just now, because on both sides, in the US are hoping to raise money for that, and in the UK we are also just now hoping to raise money to contribute to that. And that's very much an ongoing process. But we will be writing the proposal for that over the next... In fact, we'll start writing shortly after Christmas, I think, a proposal for money. We've already put in a statement of intent to our funding agency, STFC, and have been encouraged to write a proposal. So,
well, I assume that this kind of collaborative result doesn't harm in that.
Oh, I'm sure it helps, yes. No, I guess, we might hope maybe by 2020, 2021 to see an upgrade, maybe even slightly before that to the LIGO detectors, but we've just got to wait and see.
What of the other aspects of astronomy have kind of sparked your interest, particularly on this?
Well, cosmology has always interested me. How fast is the universe expanding? Hubble's constant. And of course, the whole idea of dark energy, does dark energy exist or not? And I mean, maybe we'll get a handle on that the further out we can see, to see what the expansion rate does for, once one can see much further out into the universe, using our methods rather than using supernovae as a kind of standard sirens. So, I mean, that would be very exciting. I find that very interesting because, I suppose when I started doing this kind of work, I mean, there was a great controversy about whether the universe was expanding or was it static, and the big arguments between, some of the cosmologists of that time, like Fred Hoyle and Geoffrey Burbridge, etc. And that's a lot of arguments, and that was a very exciting time because of that. Now we're seeing, of course, we're getting into a situation where we're going to be really able to properly probe these, sort of questions. Particularly with the gravitational waves, as we get more sensitivity in detectors.
You can really feel what this means for astronomy and for the astronomers themselves. I hope you've enjoyed hearing from some of the key players in this phenomenal breakthrough. If you'd like to know more about multi-messenger astronomy, you can download a free ebook from Imre Bartos and Marek Kowalski from iopscience.iop.org. Obviously, we'll post a link to that on the article for this podcast episode on physicsworld.com. And thanks so much for all your tweets and comments which keep coming in for the podcast. And thanks to JessJess98 for your lovely review on iTunes. We'll be back next month with the Physics World Book of the Year podcast, which may well be recorded in my garden shed. And thank you so much for listening.
Physics World.